Hi, welcome to the Signal Path. I have another repair video for you guys before we get back to our regular reviews. And this is actually another Fluke instrument. This is a Fluke PM6303A. This is an automatic RCL meter, so it measures resistance, capacitors, and inductors. And we've seen a lot of different types of LCR meters and so on. And this is a Fluke one, which I don't think they make anymore. But nonetheless, this was sold as a broken unit, and it's not doesn't work. It does turn on, but it doesn't really work properly. And one of the annoying things about it is that it has these mini banana plugs as the interface, and I don't have any mini banana plugs anywhere, of course, so I had to go buy some and to create my own Kelvin clips for it and so on. So that's one of the very first things I'm going to show you, and then we can actually plug something in there to see what happens and what it measures, and we'll take it apart and take a look inside of it. The surface of it is also really sticky and the buttons aren't working very well, so we may have to disassemble the front just to clean it. It has some sticky stuff on it. I'm not sure where it's coming from, but other than that, I hope that it looks nice on the inside and doesn't have any water damage or anything. But we have to start with making the Kelvin clips, and then we go from there. Here we are, our Kelvin clips. I just made these very easy and straightforward, and you got two mini bananas on this side and two mini bananas this side, and the clips on this side. So now we should be able to plug in directly to the unit and see what kind of readings we get from this. Here we go, I plugged this into the unit, so now we can go ahead and turn it on and see what happens. Let's see. There we go. Oh, 1.4. I assume that was the firmware version. All the segments of the LCD seem to be on, and there you go, it's now measuring something. It seems to be in auto mode. Let me press auto again. Yeah, definitely in auto mode, and it's reading minus 137 mega ohm. Well, that's probably not right, and it looks like it's pointing to a resistance as the dominant component that it is measuring. Let me zoom into here a little bit more. You can clearly see a few things. It says frequency 1 kilohertz, which I think it's only capable of up to 1 kilohertz, and you can see an RC combination, negative 135 mega ohm, and auto mode. So let's go ahead and short these two together, this guy and this guy. What did we get? There you go, it did something. That's promising. So something's alive in there, but it's reading 4.5 kilo ohm. Well, that's obviously not correct. It's supposed to read about 0, just over 0, but it is detecting something. So it's alive, but obviously not completely alive. And it also has another feature. It has a feature that allows the DC bias to be applied directly to the terminals to measure something that's DC operating point dependent, and a lot of capacitors are. And I can go ahead and click on, and then it will say DC bias 2 volts. Well, that's a quick way to try and see if indeed we do have a 2 volt bias. So let me get the multimeter and try that out. And as to be expected, I see nothing. So here's off, and here's on. Nope. Whatever it is, it definitely doesn't work. So something has happened to it. Now I have no idea what, obviously, because it was sold as broken. Typically, one of the ways these things get damaged is with a high discharge, because these aren't always intended to discharge the capacitor. So if you put a very large capacitor on it with a lot of voltage charged on it, it has to discharge it internally, and it can get damaged if it's not designed to safely discharge it. So that would be one thing to try out. Either way, we're going to take it apart and take a look. So I'm eager to see what's going on inside it. Alright, let's take a look. I removed all the screws. I think this is supposed to come off now. There you go, that was easy. And ta-da! Wow, it's mostly empty. I think the chassis is the same chassis that they used for the frequency counter I just repaired before this video. And as you can see, obviously there's not much in here. Everything happens over here. And the architecture is really, really simple. And look at this power switch going right across. I like this one more than that power supply that I repaired from the frequency counter, which was always on. And anyway, so you can see the display, obviously the board, there's a vertical board in here with all the display connections, and that's the input, and we're going to take a close look at it. But the architecture is very straightforward. The main transformer has our power supply. They've got some nice protection here, the earth wire properly connected, and everything looks good. We have a digital section with a microprocessor and the firmware version 1.4, as we saw. Bunch of digital 74,000 series logic there, whole bunch of op amps, and the front end right there. So we can take a look, obviously heat sinks for voltage regulators. Now I can't see much, but oh no, you know what? I see it. I see it right there. Actually, I have to move the camera, but let me show you what I just found. So if you remember, I said that one of the modes of failure is a discharge at the input, and check it out. We see some serious damage done to these resistors, and if I'm not mistaken, I'm looking through the LCD, but it looks like this capacitor here is also damaged. So this ribbon cable over here connects directly to the output and input terminals in the front, so that ribbon should come off fairly easily, and then we can examine what's going on. But clearly we have some serious damage over here. Let me look over. Wow, those resistors have seen better days. Yep, that cap is definitely dead. And I see some, what are those, LF36Ns? LF356N. Yeah, this is just typical op amps there. I have to look what type of op amp, but I'm sure I have lots of op amps to go around, and likely these are dead also. But typically there is input protection, and that's certainly some of these diodes must be Zeners around here, and these are input protection so that the large voltage of a capacitor doesn't discharge through the op amps, for example. So we have to take a look, and I happen to get the schematic, which I'm very happy, so we can actually analyze what's going on and see what these components are. And let's go back. I would say probably the best thing to do right now is to go back and take a look at the schematic, just so we understand this front end and identify what these resistors are and see if we are dealing with the discharge path. So before we repair this instrument, it's good to understand how it works. Well, let's start from basics. Before even having to worry about the block diagram and all the stuff that's schematic, let's figure out what this instrument actually needs to do. Well, it wants to measure resistances, capacitances, inductances, and so on. So it needs to have some kind of way of measuring the relationship between a voltage and the current through a component. And that's ultimately all there is to it. If you have a resistor and you put a sinusoid through it, you're going to get a sinusoid current, and the relationship between the phase of that voltage to current is going to be 0, and that will tell you that you have a perfectly resistive component. Now if you have reactive elements to that impedance, you're going to now have a phase difference between the voltage and the current through the component. You're going to have, for example, a 90-degree phase shift if it's an ideal capacitor, and so on. So if there was a way to measure the relationship between current and voltage angle through a component, then you can tell exactly what this impedance is. And this is precisely what this instrument does, and it does it in a really simple way. So let's walk through it. You start with a 16 megahertz crystal clock over here, and this is going to be the foundation for all the dynamic signals in the system. In fact, it's going to get divided to 8 meg, and that's going to feed the CPU. The CPU is going to control everything digitally, of course. So let's forget about the CPU for a second. This frequency divider is going to continue to divide the 16 megahertz signal up until it reaches 1 kilohertz. And since this is a static divider, it can generate various phases of that signal really easily, 0, 90, 180, and 270, which is not needed here. Then the signal is fed to a 1 kilohertz filter, and that filter is a bandpass filter. It's going to turn that square wave into a nice sinusoidal signal at 1 kilohertz, because you do want to apply a nice sinusoid single tone pure to your DUT in order to measure its characteristic to find out what its impedance is. And that is amplified to a large enough voltage that can be fit within the ADC range and so on. So there's an amplifier here, and this amplifier is also responsible for the DC on and off, which we just tested and in fact failed. This is what can apply the 2 volt DC offset to the component. Now you have this sinusoid, and that sinusoid is now applied to the component. Now we want to measure the relationship between the voltage and the current of that component. Now obviously this instrument cannot measure everything simultaneously. So every time it reports the measurement back to you, it's actually doing it in stages. So it will first measure the voltage at 0 degrees, then the current at 0 degrees, then the voltage at 90 and the current at 90, and it collects all that data and computes the impedance. Now, once it wants to measure the voltage and the current, there are some times 10 and times 1 multipliers and so on, but obviously you cannot sample a current, you have to convert it to a voltage first, so there's a V to I selector here. When it wants to measure the voltage, it measures the voltage directly. When it wants to measure the current, it will convert the current back to a voltage and amplify that and measure that instead. And that's what this whole section is. There's a differential amplifier and there's a programmable amplifier with various gains, so then you keep your signal always within the optimal range of the ADC, basic stuff. Once again, it's bandpass filtered at 1 kilohertz to get rid of any harmonics or hums or any other noise that might be generated, because you're only interested in the angle of the current to voltage at 1 kilohertz. And now here's where the main magic comes in. How do we know what angle we have? Well, it turns out that there is a phase sensitive rectifier, meaning that there is a rectifier in the circuit which is going to give you a DC voltage if the angle of the signal coming in, the phase of it, is coherent and exactly the same as the phase of the clock that's being fed to it. So if you're interested in measuring the component of the signal at 0 degrees, you will clock the phase sensitive rectifier with 0 degree clock, and then you can measure the coherent power between those two, and that's going to rectify and give you a DC voltage. If you change the clock to 90, degrees is going to give you a DC component at its output proportional to the 90-degree phase of the signal that's going into it. And that's what phase sensitive rectifiers mean. It will only give you a component that is locked to the phase and matches the phase of the signal that's being fed to it. And this is how we can discern between 0 and 90 degrees. So therefore, it's going to do it in multiple stages. First, it's going to be clocked with 0 degrees, measure the phase of 0 degrees, convert it to DC. Then it's going to be 90 degrees, measure the 90-degree component, convert it to DC. All of those values are going to get sampled by the ADC continuously, and I believe this ADC could be a successive approximation one, and the digital value of that goes into the CPU. The CPU will then collect all of that data from the multiple measurements, 0 degrees, 90 degrees, voltage, current, and it's going to crunch them all together and mathematically compute the impedance. And that's really easy at that point, because the impedance are phasors which you can calculate from the angle between the resistor, between the current and the voltage. And that's all that this instrument does. Now, since we know that we saw some damaged components right at the input, we can suspect the components right around here, the test voltage amplifier, the buffers, and the current to voltage converters, and the components over here is what we are interested in taking a close look at to find out where that damage has actually taken place. So let's go forward. And anyway, you can go through all this. It's really easy. In fact, this is pretty nice. This is all the math involved. That's all you need to do once you have the information about the current and the voltage angles. Then you can calculate the quality factor, the losses, the resistances, and reactance components, and all of that. Really straightforward. So let me skip forward over here. I'm sorry for going through this quickly until we see. There we go. This is what I was looking for. This is the main PCB that we were just seeing when I first opened the unit. Here's our microprocessor over here. Here's all the frequency divider, which were all 74,000 logic series. Here's the ADC control stuff, the backup battery. Here's the 16 megahertz crystal, the main crystal that I was talking about, and the EEPROM, which has the firmware on it. This is the main analog path that I was describing in terms of the different components that will measure the voltage and the current. Here's our phase sensitive rectifier, the second band pass filter, the programmable amplifier, differential amplifier. Here's the V2I selector. Here's the I to V converter. So all that stuff that's near the main inputs to the unit are suspect. And here's the backlight control, some DC supplies, plus or minus 15 volts and 5 volts, really basic stuff over there, keyboard and so on. Now, if you look here, we know which components were damaged. R101, R106 and C101 were the components that were damaged. So let's go to the schematic and see where they are and if it makes sense for them to be destroyed because of a discharge path. Now here's the schematic. Here's the front panel drive plus and drive negative voltages. Now check it out. Here's R101. Look at that. R101 is directly connected to the drive plus. And look at this path through R101, through C101, the other component that's damaged, and right over here between two protection diodes, which will prevent this voltage from going above and below these two power supplies. So if a sufficiently positive or negative voltage is applied here, you have an immediate discharge path which can destroy R101, C101, and potentially these V113 and V114 diodes. Now if you continue to look for R106, here's R106, and check it out, it's also connected to the drive plus and to two back-to-back Zeners directly connected to the ground. Another protection circuitry. If the voltage goes above and below sufficiently high enough, you have a discharge path. And since R106 and R101 are both destroyed, it points to me that there has been a discharge path. So a good place to start is to obviously replace the components that are dead and make sure that these diodes and these Zeners are still functional. It is also possible that this component, the LF356, this op-amp, is damaged, or if you continue this path, that our LF356, another op-amp down here, is damaged as part of the test voltage amplifier. So we're going to have to go through all of these to make sure these are still okay, and that we have to replace them one at a time basically, and we can test them very quickly because the first initial things to replace are really straightforward. So let's go back to the board, take that PCB out and give it a try. And here we are. I took the components out and I didn't even need to take the board out because the back of it is accessible, and here's the leftover traces there. You can see right here is where one of the resistors had exploded, so you can see it's left some mark, but we had our two resistors going across here and our capacitor going across here, and in fact those components are, let me see if I can get them on the camera, are right here, and you can see that there's definitely some serious damage to these, and I've measured them and they're completely wrong values, so they're obviously dead. So now the question is, are the protection diodes good? So let's make a couple of measurements across some of the diodes that are there just to make sure that they're still working. So let's take a look at some of these protection diodes and see what's going on. I'm going to measure one of the most basic ones at the back. What do we have here? Let's see. Ooh, that's 0 volts. I cross it. Let's see the other way around. Ooh, 0, I cross it too. And the other one? 0. Ah, 0. Jeez, these are all they're reading 0. There's a couple of reasons why that could happen. It could be that the input to the op amps are damaged. That can also short them. But you know what? I think it's safe to take the diodes out anyway and start replacing the components since we know exactly what they are. So I've already taken the resistors and the capacitor out. So let's put those back, take the diodes out, and start replacing components. And here are 2 of the diodes that I taken out that I suspect are bad. Let's give them a quick measurement here in one direction. And see, reads 0. And if I flip it in the other direction, also 0. So this is a completely dead diode. Same is true with the other one as well. Of course, I can go ahead and measure it and you shall see that indeed it is reading 0. So these diodes on the discharge path, exactly as to be expected, are dead. So now we continue moving on, measuring one component after the other in the discharge path until we see something that's working. And here we are. I put back all the components. So I actually ended up replacing obviously the 2 resistors. You can see one of them is much bigger. I didn't have a smaller one. So these resistors, this capacitor, these 2 diodes were all replaced. And they're all bad. In fact, even when they're out of the circuit, so the measurement when they were in circuit is correct. And you can tell by looking at the schematic whether that measurement would be accurate or not, because you know exactly what the pins of the diodes are connected to. So now that we're actually at the step where we can turn it back on, and see if it gives us any reasonable result. If not, then we're going to have to start suspecting the op amps. Alright, let's give it another try. And what do we see here? Oh, minus 1.5 mega ohm. That's still not right. Let me see. Let's short these guys together and see what happens now. Oh, there we go. That's actually quite a bit better. Minus 61.5 ohms. So it's obviously wrong, but it's detecting a different component. It's now detecting an inductor, which is much better, and the value is much closer. We're inching our way closer to 0. It used to say 2.4, 2.5 kilo ohm or something, but there's still something wrong. So let's go back to the schematic and take a closer look at the discharge path once again, see if there is anything else we can discover. Alright, let's measure our power supply. So there is a nice big plane of analog ground, which is this plane right here, and I'm gonna just touch on that carefully, and I can measure the different supplies. So this, I believe, should be plus 15. You know what? It would actually be very helpful if I turn this thing on. Oops, there we go. And now we're back in business. One more try. So let's get our ground bearing over there. This should be plus 15, I think. Oh, sorry, that's the plus 5 volt supply. So the plus 5 volt supply is nice and clean there. This one, there's our plus 15, looks good. This should be our minus 15, looking good. Now I want to see our plus 5 from the Zener. And I believe that's this guy. That's not good. You can see that it's actually not sitting where it's supposed to be sitting. It's quite a bit less, so it must be under a heavy load. And the other side, oh, 0. 0. This is where negative 5 should be. You see, the negative 5 is sitting at negative 0.03. So there is definitely something wrong there. Okay, that's a good sign. Well, it's not a good sign, but it's a good starting point. This means that one of the Zeners is actually bad in that power supply also. Let me give you a closer look in that. So if you take a close look at the components that I actually replaced, I replaced these diodes, these diodes over here. So that means that the discharge path has taken these out, meaning there has been some current going through these plus and minus 5 volts. Now I'm not too worried about the ground, because the ground is going to be a very wide path and it's going to have sufficient current carrying capability. But this plus and minus 5 volt I'm not so sure about. Now let's move on and see where we can find the schematic of the power supply. Sorry about that. Let me see if I know. There it is. Here we go. In fact, we have our plus 15 supply and our minus 15 supply, and check it out. The plus and minus 5 are actually generated by another pair of Zener diodes, the BZX79B4V7. So these are 4.7 volt Zeners, which makes sense. You're gonna have 4.5 volt, about 5 volt across them here, and 5 volt across this one. You're gonna get your plus and minus 5 volts. And these obviously are not intended to draw a lot of current. which means that it is possible that we have a dead supply here. Now, if the supply here is dead and is shorted to ground, then that's going to mean that the dynamic signal variation around these nodes are going to be heavily limited, so you're not going to be able to properly drive the sense voltage and so on. So perhaps that is another place where we can investigate. In fact, we should check all of our power supply voltages to make sure that they are correct and they are present. So let's go and take a look at our plus or minus 15, plus or minus 5 volt supply. That should be a pretty good starting point again. Here we can get a closer look. So here's our plus 5 volt supply, is actually labeled C. Here's plus 15, here's minus 15. And here's a Zener, one Zener over here and one Zener right under next to that capacitor. So these Zeners are all 4.7 volt and they get subtracted from the plus and minus 15. So that way the one end is connected to ground. And that way you get the 4.7 volt across each of them, creating the plus and minus 5 volt roughly. But as you saw, we're not getting that voltage. In fact, I bent that way more than I wanted to. So what we want to do is perhaps start checking those Zeners and make sure that they're dead. Let me turn the machine off, and I'm gonna set this multimeter back to measuring diodes, and everything's turned off. So now I can measure the one that I think is working. Oh, that's the wrong thing. Here we go. So this is a good one. Yeah, see, it works. 0.5 volt forward bias, and a reverse bias I will not be able to measure using the multimeter. I'm going to need the SMU. But yeah, you can see it's rising because it's got a capacitor on it. So that works. The other one, I'm measuring. See, it's 0 again. Damn it. So that Zener is also dead. And of course, that's the last piece in the discharge path. Indeed, we have another dead Zener. So that you can see that this discharge has killed everything that was in series with that went all the way through to the 5 volt supply. It's dead. Okay, let's go and replace that one too. And there it is. I replaced the Zener. Now I don't have a 4.7 volt Zener, so what I'm doing is I'm using a 3.9 volt Zener in series with a regular diode with a 0.7 volt drop on it to give me roughly what I'm looking for. I can do this because I know how this Zener is being used, and the forward junction voltage doesn't matter. They're only using it in Zener breakdown mode, so I can actually do this. So now I'm gonna go ahead and turn it on and see if you're getting our correct power supply voltages. Let's see, get this somehow so it doesn't have that much glare. There we go. I gotta turn this guy on. So we're looking for again our plus or minus 5 volt. Now this time it should hopefully be better because one of them was loading the other one. So plus 5. 4.7, that's it. So this is the 4.7 volt Zener that's already there. That was good. Remember, it was reading 3 point something before, now it's reading the correct one. And my makeshift Zener is reading minus 4.6. Not too bad. I guess I could have added a little bit more, but maybe it's something that had a slightly larger voltage, but that's the only one I had. So that looks good. It looks like our power supplies are back in business. And oh, you know what I'm just seeing? You guys can't see it yet, but let me show you the discovery. Check it out. Sorry about this terrible camera work. There you go. Now it's reading something more reasonable because it doesn't know, because it's reading capacitive. Let's short this guy together. And there you go. Perfect. It works. 0.009 ohms, which is exactly what it should be. So I should be able to measure some components to verify. But this is a really, really good sign. Actually, one other thing let's quickly measure while we are here is to see if it actually outputs the 2 volt bias that it wasn't doing that before, if you remember. So let me go ahead and trying to do this all in one shot. I apologize for the messy camera work here. There you go. So let's see if our 2 volt bias actually works and if it's accurate. Right now the bias is disabled. So it's reading, yeah, it's reading 57 picofarad, which makes sense, and it's reading 0. Let's enable the voltage. Ta-da! Look at that. Perfect. It's actually really accurate. 2.0024. It's brilliant. It works. The biasing system works now. Now we can measure some components, but I think this is it. And let's do a couple of quick measurements for the sake of completeness. Let's measure just a basic resistor. Here's a ceramic one. It should be about 10K. Let's put this into auto. There you go, 10.26 kilo ohm. Perfect. It's in fact exactly right. This Z resistor is indeed a little bit higher than 10 kilo ohm. So it looks like we can measure resistance without any issues, and it measures it correctly. What about measuring a capacitor? Here's a non-electrolytic one. It should be 47 nanofarad. and at 1 kilohertz is 45.87, and that is exactly what it should be, and it's correct. So that looks good. We can also measure a very large electrolytic capacitor, where at 1 kilohertz we won't see the exact the value that is written on the capacitor, of course to be expected because we're measuring impedance at 1 kilohertz. And we're looking at that. The effective capacitance here is 739 microfarad. That's exactly what it should be, with a quality factor of 2.28. Perfect, it's dead on. That's exactly what I would expect. And if I were to remove that, we can measure one other component. We can measure an inductor. Here's a variable one, giving us a quality factor of 0.42, which is good. We take it to this. There you go, 13.4 microhenry. That's also correct. Now I can go ahead and change the inductance by moving the ferrite core out, and thus increasing the inductance. Look at that. Very nice. It works beautifully. I think that this is definitely a unit that now can be used for future usage, and I just have to clean it up a little bit. So that's it. I think that's I explained how it works, and also we showed exactly how to fix it. So it was a very logical repair, because all you have to do is follow the path of the discharge path where someone had accidentally destroyed all the components. And the diodes, the Zener diodes, did exactly what they were supposed to do. They protected all the other components, and they give their life as they should be. So if you have any other questions, or if you have any comments, drop me a line in the comment section. I always enjoy reading what you guys have to say. I either learn something or have a chance to interact with you. If you like the video, give it a thumbs up so that other people can also find it and hopefully find it beneficial. So until next time.